Close your eyes. Let the noise of the present fall away, like dust settling in the air. Breathe slowly until you can almost hear the quiet between heartbeats. You find yourself at the edge of time. Not the end, but the beginning, the first moment after the universe has burst into being. It is young, impossibly young. A fraction of a second ago, there was nothing you could have touched, nothing you could have held. Only energy, pure, fierce, and everywhere. Now, the universe exhales. The brightness begins to cool, the heat softens from unbearable white to something calmer, darker. From that cooling, particles emerge, the smallest seeds of matter. They are not yet what you would recognize as things. They are whispers of possibility, tiny points of existence carrying charges and spins like secret codes. Among them, two will become the quiet rulers of this newborn cosmos: hydrogen and helium. Hydrogen, the simplest of all, one proton cradling a single electron. Helium, a slightly richer being with two protons, two neutrons, two electrons, balanced and whole. They drift in the vastness like shy dancers at the edge of an empty floor, unsure how to step toward each other. Time passes, not in hours or days, but in the slow rhythm of cosmic expansion. The universe stretches, space itself unfolding like an endless sheet of silk. And in that stretching, the first gentle forces begin to show their influence. Gravity, that ancient, invisible hand, draws particles together. Electromagnetism whispers, guiding electrons to circle their protons in tight, graceful orbits. The young atoms begin to sense one another, to approach, to touch. And with those touches comes something entirely new in the history of everything. Bonds? A chemical bond is not a rope or a chain. It is more like a promise, an agreement between atoms to share what they have. Electrons move between them, stitching them together with invisible threads of attraction. These bonds are not loud, not violent. They are quiet, persistent acts of connection. Here, in this calm after the cosmic storm, the first molecules appear. Two hydrogens and one oxygen, someday that will make water. But now, in this early age, most bonds form between hydrogen atoms themselves. Creating the simplest molecule, it is a pairing so basic, yet it is the foundation of what will come. Clouds, oceans, life, the space between these events is still enormous. Billions of years stretch ahead before planets will turn in their orbits, before light will fall on leaves. But the script is being written here, in these quiet unions of atoms. The chemistry of the future begins in this delicate courtship. You drift deeper into the stillness, feeling the rhythm of the early cosmos. It is not empty, though it seems so. It is humming with invisible dances, protons and electrons moving, meeting, parting, joining again. The universe is learning how to build. Every bond is a sentence in a new language, a language of form and structure. Some atoms join in pairs, others in small, fragile clusters. These are the precursors of clouds that will someday condense into stars. For now, the dark stretches on, the only light, the faint glow left over from the birth of everything. That glow, the cosmic microwave background, will someday tell astronomers the exact age of this moment. But tonight you are simply here, floating in its gentle warmth. You imagine reaching out to touch a molecule. It would not feel like anything familiar, not soft, not hard, not warm. It is too small for your senses to hold. And yet, it is real, and it is the reason anything else can ever exist. Hydrogen and helium continue their slow, patient drift. They are carried on waves of gravity, collecting into great clouds that span light years. In those clouds, density builds. Atoms are pulled closer and closer until the distance between them is small enough for something astonishing to happen again. Fusion. Fusion is a different kind of bond, not a quiet sharing of electrons but a merging of cores. When two hydrogen nuclei fuse, they become helium, and in the process, they release light and heat. This is the birth of the first stars. The stars flare into being like lanterns lit in the darkness. Their light travels across the black, touching distant clouds and warming the emptiness. Within their hearts, fusion continues, creating new elements: carbon, oxygen, nitrogen, the letters of a much richer chemical alphabet. Some stars will live long, gentle lives, burning steadily for billions of years. Others will burn hotter, faster, collapsing into themselves in brilliant supernova. In those moments of collapse and explosion, even heavier elements are forged: iron, gold, uranium. Everything you will one day touch, wear, or breathe is being made here in the quiet violence of stellar life. You drift among them, weightless, feeling the pulse of creation all around you. Every sparkle of light is a workshop, every cloud a waiting story. And still, the bonds that hold matter together, those tiny promises between atoms, remain the foundation of it all. Without them, there would be no stars, no planets, no water, no you, just endless particles drifting forever apart. But with them, the universe learns how to gather itself, how to shape, how to grow. You sense now that chemistry is not just the study of matter, it is the study of relationships. It is the gentle art of attraction and sharing, scaled up to the size of galaxies and down to the size of molecules. The same forces that bring two hydrogen atoms together also shape worlds and breathe life into them. Somewhere, billions of years from this moment, on a small rocky planet around an ordinary star, a person will hold a pebble in their hand and wonder how it came to be. And the answer will trace back here, to the first spark of bonding, the first quiet agreements between atoms. The universe will keep expanding. Stars will live and die, scattering their elements like seeds on the wind. Clouds will form again, and new stars will ignite, carrying the cycle forward. It is a rhythm without hurry, without end, and as you float in this deep, slow beginning, you notice something else. The language of these early bonds will not remain hidden. It will grow more complex, more expressive, until atoms can tell entire stories just by the way they link. Stories made of carbon chains, of crystalline lattice, of water's flowing geometry. Stories you will someday read not with your eyes, but with your fingertips, your breath, your life. And so, from this first spark, another question begins to form, one that will follow you into the next part of your journey. If the universe can speak through the bonds of atoms, what does it sound like when matter learns to speak to itself? You are still drifting in the dark spaces between newborn stars. Their light is young, their heat still spilling out into the vastness, but your attention now turns from the grand sweep of galaxies to something smaller, the scale of the invisible, where bonds are not just accidents of closeness but purposeful conversations. An atom is not silent. It holds within itself a structure, a rhythm that repeats and repeats, protons and neutrons at the center, electrons moving in their wide, looping paths. If you could listen closely enough, each electron's movement would sound like a faint tone. And note, in a cosmic scale, atoms are not all alike. Hydrogen, the simplest, carries just one note, clear, bright, like the ringing of a single bell. Helium adds another, deeper resonance, its stability giving it a quiet, steady hum. As atoms grow more complex, carbon, oxygen, nitrogen, their notes multiply and weave into chords, intricate harmonies that make the universe's music richer. But music only becomes a song when notes interact. Here, interaction comes through the dance of electrons. Electrons are the couriers of chemistry, the ones who decide if atoms will stay apart or come together. They do not collide like stones. They reach for one another, forming shared clouds. Where their presences overlap, these shared spaces are the bonds you first saw in the universe's early days. But now you begin to notice the subtleties. Some bonds are covalent, a partnership where electrons are shared equally, as if two atoms clasp hands and walk side by side. Others are ionic, a transfer of electrons, where one atom offers its electron as a gift and the other accepts, holding it close. There are metallic bonds, two vast, shimmering arrangements where electrons roam freely, slipping from one atom to another like guests at a long banquet table. Each kind of bond has its own tone, its own place in the orchestra of matter. And when you pull back just far enough, you can see these tones shaping the properties of the materials around you. The hardness of diamond comes from carbon atoms locked in a rigid, three-dimensional embrace. The softness of graphite, also made of carbon, comes from layers of atoms sliding gently past each other, like pages of paper. The difference is not in the atoms themselves, but in the way they speak and listen to one another, you breathe slowly. Even here, in the language of the smallest scales, there is a patience, a slowness. Atoms do not hurry to bond. They move according to their energies, their charges, their surroundings. Each meeting is a negotiation. You begin to notice patterns in these conversations. Some atoms, like noble gases, helium, neon, argon, prefer to remain silent. Their outer electron shells already complete, their music self-contained. Others, like oxygen or fluorine, are eager to connect, seeking partners to complete their outer shells. And then there is carbon, versatile, adaptable, able to bond with many others, weaving complex structures like a poet weaving verses. As you drift through this atomic world, you see the first signs of complexity emerging. Simple molecules, hydrogen gas, oxygen gas, nitrogen gas, combine in new ways, two hydrogens and one oxygen forming water, carbon and oxygen forming carbon, dioxide, nitrogen, and hydrogen creating ammonia. Each combination brings new properties, new possibilities for matter to behave in ways no single atom could achieve on its own. You can feel, in the background, the slow build toward something larger. This is not just structure for structure's sake. This is the groundwork for life, though life itself still lies far in the future. For now, the molecules drift in clouds, in oceans of gas and dust, waiting for the next step in the cosmic story. The more you listen to this language of atoms, the more it feels familiar. It is not unlike the language you speak or the way music moves through you. There are rules, grammar, syntax, rhythm, but there is also freedom. Moments when atoms connect in ways that surprise even the stars that forged them. If you were to reach out and hold a grain of sand, its solidity, its texture would all be the result of these atomic conversations locked into place. Silicon and oxygen, bound tightly in repeating patterns, whispering to one another across invisible bonds, giving the grain its shape, its resistance to your touch. You begin to see the truth. Chemistry is not a static thing. It is alive with movement, not frantic, not hurried, but constant and certain. Electrons move, bonds form and break, atoms rearrange themselves into new alignments. This is how change happens at the most fundamental level. Some changes require energy, a push to break the old bonds and form new ones. Others release energy as if the atoms have found a more comfortable arrangement, settling into a lower, gentler state. These exchanges of energy are the quiet heartbeat of the physical world. You float further, watching molecules grow in complexity, from simple pairs and trios to long chains, rings, branching patterns. In the chemistry of space, these molecules gather on dust grains, coat them in icy layers, and ride comets into the waiting arms of planets. It is here that the seeds of oceans, and perhaps of life, are quietly sown. The language of atoms is everywhere. In the air you breathe, in the rocks beneath your feet, in the blood that carries oxygen through your body. It is a language written not in letters, but in forces and arrangements. In invisible architectures, you sense now why the universe began with bonds. Without them, there would be no conversation between matter, no possibility for growth or complexity. With them, every new molecule is a phrase, every reaction a sentence, and the sum of them all is a story as vast as the cosmos itself. Your breath slows. Somewhere ahead, this language will give rise to something even more remarkable. Not just the ability of matter to speak, but the ability of matter to connect across great distances, to carry information, to flow and change without losing itself. And so, as you drift away from this quiet chorus of atoms, you feel a new question forming, a question that will lead you to the next chapter of your journey. If atoms can speak, what happens when their voices join into the flowing chorus of water, the great connector of worlds? You follow the thread of your last thought. If atoms can speak, what happens when their voices join into something fluid, something that moves through the world with ease? You open your eyes, and there it is. A bead of water clinging to the edge of a leaf, perfectly curved, catching the morning light in a way that makes it seem as if it holds the sun inside itself. It looks simple, transparent, and yet, Water's story is one of the most intricate in the universe. The droplet is made of countless molecules, each one two hydrogens and one oxygen, joined in the shape of a tiny bent letter. This shape matters. It is what gives water its gentle polarity, a slight imbalance in charge that lets one side whisper to another molecule, "Come closer." The result is a web of invisible connections, hydrogen bonds linking each water molecule to its neighbors. These bonds are not as strong as the covalent ones that hold the atoms together inside the molecule, but they are strong enough to give water its unique character. You notice how these hydrogen bonds make the droplet hold its shape as if the surface were a thin skin. This is surface tension, and it's why water can beat on a leaf. Why small insects can walk across a pond without sinking. You breathe slowly, and your mind drifts to a mountain stream where water slips over rocks, curling into eddies, splitting, rejoining, never losing itself. Water is a connector. It moves between states with grace, from liquid to vapor to ice, carrying heat, carrying life, and yet it is more than a traveler. It is also a dissolver, able to take other molecules into itself. Salt, sugar, minerals. Water pulls them apart, surrounds their ions, and carries them away. Because of this, it becomes a medium for exchange. Nutrients flow through roots into plants, through blood into cells, all because water is willing to hold what others cannot. You imagine a single drop falling into a pond. The ripples spread outward, but so does the chemistry, molecules drifting, meeting others, making new combinations. In the oceans of the early Earth, this was everything. It was here that the building blocks of life could mingle and meet. Encouraged by the gentle hand of the waves, the warmth of the sun, and the patient work of time, you feel your own body. Now, the steady rhythm of your heartbeat, the quiet movement of your breath. You are mostly water. It fills your cells, flows in your blood, cushions your joints, keeps your temperature steady. It connects the distant parts of you, just as rivers connect distant parts of the land, but water's gift is not only to life. It shapes the planet itself. Rain falls on mountains, breaking rock into soil. Rivers carve valleys. Ice, expanding as it freezes, splits stone apart. Over millennia, water redraws the maps of continents. Even in the air, water moves quietly in. Its vapor form, forming clouds that carry it across the world. A molecule of water that falls on your hand today might have been frozen in an Arctic glacier a century ago, or swirled in a tropical storm thousands of miles away. You think of how easily water moves between forms. A liquid becomes vapor with the touch of sunlight. Vapor becomes ice when the air grows still and cold. And yet, through all these changes, the water molecule remains the same. The bonds inside it do not break, only the bonds between. Molecules shift and rearrange. This is the secret of water's endurance, change without losing identity. It flows, it falls, it rises, but it remains itself. A lesson written in every river, every cloud, every glass you have ever lifted to your lips. Now you picture the oceans of Earth, their surfaces stirred by wind, their depths cold and dark. In them, water carries heat from the equator to the poles, driving currents that shape weather and climate. Without this, the planet would be a harsher, less forgiving place. You imagine drifting in those deep waters, light fading above you, until you can see only the faint glow of creatures who make their own illumination. Even here, in the most remote darkness, life depends on water. It fills the bodies of these creatures, carries oxygen to their cells, removes the waste of their living. Water is not only a connector of places, but of times. The water in your body now is ancient. It has passed through rivers, through clouds, through the roots of trees and the veins of animals. It has been rain, ice, vapor over and over again. You hold your breath for a moment, thinking of how each inhale brings in molecules of water vapor that may once have been part of a storm over an ocean, or a droplet in a glacier, or a tear on someone's cheek. And so water carries stories. It is the great archivist, preserving the memory of the earth in its endless cycle. The droplet on the leaf slips free at last, falling toward the soil. It will sink into the roots of a plant, rise again through the stem, evaporate into the air. And perhaps one day fall as rain on another leaf. On another morning, you realize now that water's gift to life is not only that it connects, but that it teaches. It teaches that nothing is truly separate, that all things are in quiet exchange. You let this thought settle, and notice the way it leads naturally to the next question. If water can carry the ingredients of life across the world, what happens? When those ingredients begin to burn with a slow, steady flame inside living cells, you carry the thought of water's endless cycle with you, how it gathers, moves, and delivers what life needs. Now you step closer to life itself and discover another current, another quiet but powerful flow. Energy. Every living thing is an island of order in a universe that tends toward disorder. To hold that order, to build and repair and grow, life must gather energy and release it in just the right way. You know the fierce heat of fire, how it leaps and devours, how it transforms wood to ash in moments. But the fire of life is different. It is slow, measured, contained within the boundaries of cells. You take a breath, already the chemistry begins. Oxygen moves into your lungs, crosses into your blood, and rides to the trillions of cells that make up your body. There, it meets fuel, molecules of sugar and fat, each one a package of stored sunlight, captured long ago by plants through the quiet work of photosynthesis. Inside your cells, in tiny structures called mitochondria, these fuels are unpacked, their bonds broken in a careful sequence. With each step, energy is released, not in an uncontrolled burst, but in pulses, as if the cell is taking slow, steady sips rather than gulping all at once. This is cellular respiration, and it is the slow fire that keeps you warm, that powers your muscles, that lets your mind shape thought into words. You imagine it now, the delicate machinery of enzymes guiding each reaction, passing electrons down a chain like runners in a relay until they meet oxygen and form water once again. Even here, water is part of the cycle, appearing as both product and participant. The energy released is captured in molecules of ATP adenosine triphosphate, small, portable batteries used for almost every task in the cell. They are spent and remade thousands of times a day, a rhythm so constant you never feel its individual beats. Only the life it sustains. Life's slow fire is not limited to animals. Plants burn too, though they gather their fuel differently. In the green depths of their leaves, chlorophyll captures sunlight and uses it to build sugars from carbon dioxide and water. This is photosynthesis, the other half of the grand exchange. Plants store the sun's warmth in chemical bonds, and animals, eating plants or one another, release that stored energy back into the flow. It is an unending cycle. Light becomes sugar, sugar becomes movement, movement becomes heat, and heat drifts out into space. You think now of a seed lying dormant in the soil. From the outside it seems lifeless. Inside, though, the potential is waiting. When water soaks in and warmth surrounds it, the seed's slow fire begins to stir. Molecules shift, ATP is made, cells divide, and a green shoot pushes upward, drawn by light it cannot yet see. Even in the cold deep of the ocean, where no sunlight reaches, life burns in its own way. Around hydrothermal vents, bacteria take the chemical energy from minerals in the Earth's crust and turn it into fuel. From that fuel, entire ecosystems rise. Tube worms, crabs, fish, each one part of the same patient chemistry. The slow fire of life is everywhere. In the twitch of a bird's wing, in the silent expansion of a mushroom in the night, in the steady beat of your own heart. It is not separate from the fire of the stars. The energy in your cells is the same energy that once flared in the core of the sun, traveled as light across space, and was caught by a leaf. You realize now that you are not only carried by life's chemistry, but made of it. Your cells hold the same patterns that life on Earth has used for billions of years. The enzymes, the cycles, the bonds, they are as old as the first bacteria that floated in ancient seas. You picture that first spark of metabolism, a cluster of molecules that found a way to use energy to make more of themselves. From there, the slow fire spread, adapting, diversifying, until it filled the oceans, crawled onto land, took flight in the air. And now, here you are, breathing in, burning gently, breathing out. It is humbling to think that this constant chemistry is not something you must control consciously. Your cells know the steps. They keep the fire alive whether you are running, reading, or drifting towards sleep. You begin to see life not as something separate from the rest of the universe, but as the way the universe has found to keep certain fires burning longer, more steadily, more purposefully, and yet this fire requires more than just fuel and oxygen. It needs structure, the quiet scaffolding that gives form to flesh, that holds shape against the pull of gravity. Without that structure, the fire would have nowhere to live, which leads you to the next step in your journey. If life's chemistry is a fire, what shapes the hearth that holds it? You carry the image of life's fire in your mind, a steady, quiet burning in the hearth of the cell. But for a fire to burn, it needs a container, a structure that holds its form in the world of matter. Structure is born not from bricks or beams, but from molecules, invisible architects, assembling patterns that determine what a thing will be, how it will feel, and how it will live. Among these architects, one stands apart: carbon. It is not the most abundant element in the universe. Hydrogen, helium, oxygen all outnumber it. But carbon has a gift that makes it the quiet champion of complexity. A carbon atom can form 4 bonds at once. This gives it the freedom to link with other carbons, to create chains, branches, and rings in endless variety. No other element can match its flexibility, its willingness to connect. You imagine carbon atoms like builders in an open field, handing tools back and forth, joining together into long scaffolds, then weaving side branches and looping them into shapes that will one day become the skeletons of living things. In diamond, carbon atoms are locked in a 3-dimensional lattice, each one bonded strongly to 4 others. This perfect repeating pattern gives diamond its unmatched hardness, its ability to bend light into sharp, glittering rainbows. In graphite, the same carbon atoms arrange themselves in flat sheets, each sheet able to slide over the next. This softness, this willingness to move, lets graphite leave its mark on paper, turning invisible bonds into visible words. The lesson is clear. It is not just the ingredients that matter, but the design. The same atoms, arranged differently, can make something unbreakable or something that crumbles between your fingers. Carbon does not build alone. Oxygen, nitrogen, hydrogen, sulfur, phosphorus all join the work, each bringing its own skills. Oxygen's strong pull on electrons can create polar bonds that give molecules shape and reactivity. Nitrogen, with its ability to form 3 bonds, adds new dimensions to molecular structures. Sulfur can link distant parts of a molecule, creating loops and knots that change how it behaves. These elements together create the molecules of life, proteins that fold into intricate shapes, DNA that coils like a long, patient story, lipids that form the boundaries of cells. Proteins, especially, are masterpieces of molecular architecture. They are built from chains of amino acids, each one a small, unique block. The order of these blocks is like the order of letters in a word. Change the sequence and you change the meaning. Once built, the protein chain folds into a specific shape, its creases and curves perfectly suited for its job. Some proteins are enzymes speeding up the chemistry of life. Others are structural, like collagen in your skin or keratin in your hair. All of them owe their abilities to the invisible architects that place their atoms with such precision. Beyond life, molecular architecture shapes the non-living world. 2. Minerals form when atoms arrange themselves into crystals, patterns that repeat over and over until they grow into visible shapes. Salt crystals form cubes, quartz forms hexagonal prisms. Snowflakes grow in delicate 6-pointed symmetry, each one unique but all following the same quiet rules. You think now of silk, spun by a spider in the night. Its strength comes from proteins arranged into fibers that are both tough and flexible. The spider does not think in chemistry, but its body knows how to gather amino acids from its food, how to weave them into proteins, how to fold and align those proteins into a thread stronger than steel by weight. Molecular architecture is not static. It adapts to conditions, responds to forces. Bones, for example, are constantly being rebuilt, old material broken down, new material laid in place. This remodeling keeps them strong, able to bear new stresses, even at the planetary scale. Molecular structures shape landscapes. The crystalline structure of ice makes it less dense than liquid water, so it floats, a small miracle that allows oceans to freeze from the top, protecting life beneath. The silica structure in sand makes it resistant to weathering, allowing beaches to endure against the waves. You realize now that every texture you have ever felt, every surface you have ever touched, was determined by molecular design. The smoothness of glass, the grain of wood, the brittleness of chalk, all are the signatures of atoms arranged in their particular ways. Carbon still lingers in your thoughts. Its four bonds like open hands, always ready to connect. It is in the graphite of your pencil, the sugar in your tea, the DNA in your cells, the fuel in your breath. It is the quiet backbone of life and matter, building without pause, and yet structure alone is not enough. To build a world, you need not only the architects but also the air between the walls, the space where exchange can happen. You need the breath that moves through the spaces molecules create, which leads you to your next question. A question the air itself will answer. If molecules can build the walls of the world, what chemistry flows in the spaces between? What is the language of the air you breathe? You stand now in an open field, and for the first time in this long journey, you notice the space around you. It is not empty. It is full of invisible travelers, full of the quiet chemistry of the air. You take a slow breath. The air slips in, cool and weightless, filling your lungs, spreading into your blood. In a moment, oxygen molecules will ride to every corner of your body, feeding the slow fire within your cells. Oxygen is only one voice in this great chorus. Most of what you breathe is nitrogen, a calm, steady gas that makes up about 78% of the atmosphere. Nitrogen does not burn easily, does not react quickly, but it is essential to life. In the right chemical hands, in the roots of certain plants, or in the labs of lightning storms, nitrogen is woven into amino acids and DNA. The very threads of living structure. Oxygen, about 21% of the air, is far more reactive. It fuels your metabolism, allows wood to burn, rust to form, rocks to weather. Its energy is both life-giving and life-ending, capable of nourishing a body and also breaking it down. The rest of the air is a scattering of other gases. Argon, quiet and noble. Carbon dioxide, the messenger between breath and plant. Traces of neon, helium, methane, and ozone. Each molecule has a story, a journey that spans oceans and centuries. When you breathe in, you are pulling in molecules that have been inside countless other lungs, human, animal, even the hollow spaces of leaves. Some may have circled the globe many times, riding currents high above the earth. Others may have risen yesterday from the dark depths of the ocean. Air moves constantly, a restless river without banks. It carries pollen across continents, salt from sea spray into mountain valleys, ash from volcanoes into sunsets thousands of miles away. It brings warmth from the tropics to the poles and cold from the poles to the tropics. The chemistry of the air changes with the day, with the season, with the turning of the earth. After rain, the air carries the scent of petrichor, compounds released from the soil. In a forest, it is rich with terpenes from the leaves. Near the ocean, it tastes faintly of salt. Each breath you take is more than just oxygen in, carbon dioxide out. It is an exchange. Your body gives to the air what plants will take in, and plants give back what you will breathe tomorrow. It is a loop, a conversation without end. You think of the first breaths on Earth, billions of years ago. The air was thick with carbon dioxide and methane. Life then was microscopic, and it shaped the atmosphere slowly, molecule by molecule. Cyanobacteria began to release oxygen through photosynthesis, and over millions of years, that oxygen built up in the air. It was a revolution, one that allowed complex life to emerge, but also changed the course of the planet forever. Now, oxygen and nitrogen are the pillars of the air, but carbon dioxide, though only a trace, plays an outsized role. It holds heat in the atmosphere, warming the planet just enough for life to thrive. Too little, and the earth would be a frozen desert. Too much, and the warmth would become unbearable. The air is not just a mix of gases. It is a stage for constant chemistry. Water vapor condenses into clouds, releases rain, or freezes into delicate ice crystals. Ozone forms high above, shielding the surface from the sun's harshest rays. Dust particles gather moisture, seeding the first drops of a storm. If you could see the molecules, you would watch them dart and spin, colliding, separating, trading energy in an endless, chaotic ballet. Each one moves at hundreds of meters per second, yet the space between them is vast on their scale. They are fast, but they are light. You can feel their combined touch as only a soft breeze. You think now of wind. Air set in motion by the uneven heating of the earth. The sun warms land and water differently, and air moves to balance the difference. This movement carries seeds to new ground, spreads scents and songs, and shapes the weather you feel on your skin. Your own breath becomes part of this movement. Exhaled carbon dioxide will join the wind, circle the earth, perhaps settle into the ocean, or be drawn into a leaf to begin the cycle again. The air connects you not just to the present moment, but to the deep past. Some of the oxygen you breathe was made in stars that exploded long before the sun was born. Some of the nitrogen in your body was fixed into form by bacteria hundreds of millions of years ago. The atmosphere is a shared inheritance, passed down from every living thing that has ever existed. No one owns it, yet everyone shapes it. You. Take another breath now, slowly, letting the air fill you. You imagine each molecule's journey, the hands, or leaves, or fins, or wings. It has touched. It is humbling, knowing that the space around you is not just emptiness, but the meeting place of worlds. The air does not keep still. It flows between sky and sea, between the warmth of day and the chill of night, carrying the chemistry of life wherever it goes. And yet, as much as the air moves and mingles, there are things that resist its touch. Solids with their fixed shapes stand against the wind, holding still in a moving world. Which brings you to your next question. If the air is the breath between worlds, what is the stillness that gives shape to them? You step from the restless air onto the steady ground beneath your feet. It feels unchanging, immovable, a kind of anchor in the flowing world. Yet even here, in the cool hardness of stone, there is movement. It is not the rushing dance of gas molecules nor the flowing currents of liquid water, but a subtler, slower vibration, atoms holding their places, yet trembling gently in their bonds. This is the language of solids. It is a language of arrangement, where the position of each atom and the bonds that link them decide the nature of the whole. In a crystal, this arrangement is perfect and repeating. Atoms line up in patterns that extend in all directions, like a design woven without flaw. Salt forms neat cubes. Quartz grows in hexagonal prisms. Snowflakes branch into six-fold symmetry, each one shaped by the temperature and humidity of the air in the moment it formed. In other solids, the order is less perfect. Glass, for example, is a frozen liquid, its atoms locked in place before they could fall into a crystalline pattern. This irregularity gives glass its transparency and brittleness, its quiet fragility. You run your hand along the surface of a rock. The texture you feel, smooth or rough, grainy or polished, comes from how its minerals grew. From the crystalline architecture and the spaces between, solids hold their shape because their atoms are tightly bound. Each one is connected to its neighbors by bonds strong enough to resist the pull of gravity, the push of wind or water. It is this resistance that lets mountains stand for millions of years, that lets the cup in your hand hold tea without spilling, and yet solids are not entirely rigid. Push hard enough and the bonds can stretch or shift. Metal bends under a steady force. Wood flexes in the wind. Even stone will fracture if the stress is great enough. Some solids are crystalline, their internal order giving them strength and predictability. Others are amorphous, their atoms arranged more like a frozen crowd, random but close-packed. The difference between the two is a difference in how they speak the language of form, one in precise repetition, the other in adaptable irregularity. Temperature can change the conversation entirely. Warm a solid and its atoms vibrate more, strongly pushing against their bonds. Cool it and the vibrations slow, the structure tightening. If you add enough heat, the bonds can break and the solid becomes a liquid, slipping out of its fixed form. You think of ice, water's solid. Voice. Its crystalline pattern pushes molecules farther apart than in liquid water, making it less dense so it floats. This single detail means that ponds freeze from the top, allowing life to endure beneath the ice in winter. Some solids are born from heat. Magma cools into basalt or granite, its minerals locking into place as they lose energy. Others are shaped by pressure, like coal compressed into diamond deep within the earth. Some are built slowly, molecule by molecule, like the shell of a mollusk or the skeleton of a coral reef. Solids are the bones of the planet. They form mountains and cliffs, roads and shelters, tools and sculptures. They give you something to push against when you walk, something to lean on when you rest. And yet their stillness is an illusion. On the atomic scale, every atom hums with energy. They shift slightly, trading vibrations with their neighbors. In metals, electrons move freely, carrying heat and electricity through the structure. In semiconductors, the arrangement of atoms controls whether electricity flows or stalls. Even the most familiar solids hold surprises in their form. The graphite in your pencil is made of carbon atoms arranged in sheets, while diamond, also carbon, locks those atoms into a rigid lattice. Same element, two entirely different languages of form. You picture a building, its walls made of bricks. Replace each brick with an atom, and you begin to see how solids are built from the ground up. Change the pattern of bricks or the way they connect, and the building's strength, shape, and use will all change. Solids teach patience. They are formed over years, centuries, millennia. A tree lays down one ring each year. A stalactite grows just a few centimeters in a century. The Earth's crust drifts slowly, mountains rising and wearing down in cycles that span millions of years, and yet for all their endurance, solids are also temporary. Given time, stone will crumble to sand, metal will rust to flakes, bones will turn to dust. Form is never truly permanent, only slower to change than the wind or the wave. You sit now on a large, flat rock. It feels solid under you, its form holding your weight with ease, but you know it is not truly still. Its atoms vibrate, its minerals expand and contract with each change of temperature. Rain will one day find its cracks, freeze and expand, and split it into pieces. The rock is patient. It does not hurry to change, and in that patience you feel a quiet strength. But solids are not the end of the story. For all their stability, life cannot flow through them as it flows through air or water. To move, to carry, to connect, you need something different, something that slips between forms, changing without losing itself. And so your thoughts turn back to the beginning of this journey, to the bonds that first pulled atoms together, to the molecules that carried life's spark, to the invisible dance that never stops, which leaves you with the final question. If matter can be still and matter can flow, what binds it all into the endless cycle of change? You sit on the rock a little longer, watching the slow colors of the sky change as the light softens toward evening. The rock will still be here tomorrow and the day after, but you know now that even this patient shape is moving through time. Everything? As you breathe in and the air carries oxygen into your blood, that oxygen joins your cell's slow fire, turning sugar into energy, energy into movement and warmth. The byproducts, carbon dioxide and water, slip back into the air, ready to be used again by leaves and oceans. Nothing is lost, nothing stays exactly the same. This is the chemistry of cycles. It is the way matter passes from one form to another, over and over, writing time not in hours or days, but in transformations. You think of the carbon cycle. A carbon atom in your breath. Today might have been in the shell of a clam 1,000 years ago, or in a leaf just last summer. It might have drifted in the air as carbon dioxide, been caught by a green leaf, woven into sugar, eaten by an animal, and carried in muscle before returning to the sky. Or the water cycle, the droplet on the leaf you saw days ago falling to the Soil, sinking to an underground stream, flowing into a river, reaching the ocean, evaporating into a cloud, and falling again as rain on a faraway mountain. Cycles run through everything. The nitrogen cycle that feeds the soil, the rock cycle that builds and breaks mountains, the slow churning of tectonic plates, the endless flow of energy from the sun through the living and back into space. Each cycle has its own rhythm. Some turn quickly, like the daily rise and fall of water in a tide. Some take millennia, like the transformation of limestone into marble. Chemistry is the pen that writes these rhythms. Bonds form and break, atoms rearrange, heat moves from one place to another, and the story continues. You realize now that time is not something outside of matter. It is not just the ticking of a clock. Time is written into matter's changes. In the growth of a crystal, the rusting of metal, the folding of a protein, the fading of a leaf, even you are part of this writing. Your body is a temporary arrangement of ancient atoms, borrowed from the earth and the air. One day, those atoms will return to the cycles, to be part of something else, a tree, a stone, a wave. There is comfort in this. It means you are not separate from the world's flow, but part of its constant renewal. Some cycles run on human time, others on the planet's time, others still on the universe's time. The calcium in your bones was forged in the heart of a long-dead star. The iron in your blood traveled through space for billions of years before finding a home in your body. Even the atoms themselves are ancient, older than the earth, older than the sun. They have passed through countless forms, and will pass through countless more. You think of decay not as an ending, but as a handoff. When wood rots, its carbon feeds fungi and insects. When a mountain erodes, its minerals feed rivers and plains. When a star dies, its elements seed new worlds. Cycles are not perfect circles, but spirals, each turn reshaping what came before. The oxygen you breathe today is not exactly the same as it was when the first forests grew. It carries traces of all that has happened since, a chemical memory of the planet's journey. In this way, chemistry keeps time for the Earth. Ice cores hold layers of ancient air, telling stories of climate long past. Rocks record the shifting balance of elements in seas that vanished millions of years ago. Even the rings of a tree are chemical records, marking years of drought or abundance. Time moves forward, but cycles fold the past into the present. Every molecule carries history. Every atom has been somewhere else before. You let this thought settle, feeling the slow heartbeat of the planet beneath you. The cycles will continue long after you are gone, just as they began long before you arrived. This is not a loss. It is a kind of belonging that does not end. You picture the rock beneath you returning, one day to sand, the sand carried to the sea, the minerals drawn into the shells of living things. One day, perhaps, those shells will harden into new rock, and the cycle will turn again. Above you, clouds drift, their shapes changing even as you watch. They will rain, the rain will flow, and the river will carry the story onward. In the end, there is no true beginning or end, only transformation. Only the steady rewriting of matter's arrangements, life's borrowing of atoms, the universe's patient rearranging of its pieces. And as you close your eyes, you understand something simple and vast. You are not outside this story, you are a chapter in it. You are a moment in the chemistry of the world. When your moment passes, your atoms will keep moving, your molecules will find new shapes, and the cycles will carry you forward into forms you cannot yet imagine. The endless cycle will write on, and you will be part of every word.